Okay, I'm back. So yeah, a lot of traveling, very tired, but yeah, come back to learn Rust because otherwise it takes forever. Hmm. And my coffee is getting cold. So yeah, so let's jump into it. Functional program fun. Oh, oh, this is our mini grip. Okay, I remember what's going on. Okay, so functional language features, iterators and closures. So cool. Chapter 13. Finally, we got to learn what is iterator. So, Rust design has taken inspiration from many existing languages and techniques. One of them is functional programming, and programming is a functional style that includes using function as value by passing them in arguments, returning them from other functions, assigning them to variables for later execution, and so on. We won't debate the issue of what functional programming is or isn't, but instead discuss some features of Rust. They're similar to features in other languages, often referred to as functional. We have that in Python as well. It's not a very uncommon thing, but yeah, of course you can debate about whether we should do it or not, but it's fine. And yeah, so function like constructions, you can store. So we have closures. There's a function like structured you can store in variable. I think. Well, I don't know what it is. I think I have to look into what it is. Like closure is closure, but like, what are we using it here? I don't know. Iterators, we've seen it a lot. How to use so iterator is a way of processing a series of elements. How to use closures in iterator to improve the I/O project. In chapter 12, we'll go back to that later. Performance of closure and iterators. Spoiler alert. They're faster than what you may think. Okay. Already covered some other Rust features such as pattern matching in so influenced by the functional style, because mastering closures and iterator is important part of writing idiomatic fast Rust code. Devote this entire chapter to them. Yep, so let's look into it. Closures, anomalous function that capture the environment. So Rust closure are anomalous functions you can save in a variable, pass as an argument to other functions. You can create the closure in one place and then call the closure somewhere else to evaluate it. In a different context, unlike functions, closure can capture values from the scope in which they are defined. We would demonstrate how these closure features allow for code to reuse and behavior customization. Cool. Yeah, I think like we've seen a lot of closures, but kind of I never thought very deeply about it, so I think it's cool that we come into this. And capturing the environment with closures. Every so often a t-shirt company give us an exclusive limited edition shirt to someone on our mailing list as a promotion. People on the mailing list can optionally add their favorite color to their profile. If the person chosen for free t-shirt has their favorite color set, they get that color shirt. If that person hasn't specified his favorite color, they get whatever color the company currently has the most of. There are many ways to implement that. For example, we're going to use an enum called shirt color that has red and blue. Yeah, so very simple. We don't have, well, otherwise you can have a million colors, but we represent a company's inventory with an inventory struct that has field names shirts that contains a VAC representing the shirt color currently in stock. The method give away defined and on inventory gets the optional shirt color preference for the free shirt winner. Okay, so yeah, we have the struct, we have the inventory, and enum, and then we have the struct inventory, and the inventory will have a giveaway function that will find which one to give away. It's either user preference or most stocked. And wrap or else, I think if it's none or like it doesn't exist, then we'll have to use this because it's unwrap or else. Most stock is doing this. Red and blue. So the color in self shared mesh color. So this is checking the shirt piles. How many shirt do we have? Like, and what color? Which color? Then we would count. Basically, it's counting the stack of how many red, how many blues. If red bigger than blue, then yeah, then it's easy. If we have just two, yeah. So in main, then we have the inventory. So these are the pile of shirts, and then giveaway. If it's none, then it will have yeah. Okay. So now we run the code. So we can we just run the want to create this project? Are we going to reuse it? Maybe we just look at it for now. So if we run the code, we will print if user with preference some red gets red, if user with preference none get blue. So this most stock is a closure on the inventory instance. The standard library didn't need to know anything about the inventory or shirt color. Type we define, or the logic we want to use in this scenario. The closure captures a immutable reference to the self inventory instance and pass it with the code. We specify the unwrap or else method. Function, on the other hand, are not able to capture the environment in this way. So what is this like most stock different from just a normal function? Because it's called unwrap or else, and then this is most stocked. So the closure, this is closure expression because we have these like two pipe operators. This horizontal, vertical line here are defined by standard library. Yes. Take one argument, a closure without any argument that returns. So it will take a closure in the unwrap or else, and then it will take a closure without any argument that returns a value t. The type stored in the sum variance of option t. Yeah, because this is returning the type inside sum, which is the shirt color, right? So yeah, so it will be unwrap or else. Then this also needs to be the same type, which is the shirt color. In this case, yeah, shirt color. If option T have some variant, yeah, if there's some, if not, then we'll call the closure and return the value. So this is different because the unwrap or else method doesn't know what's going on inside, and it's kind of like a self environment that it doesn't matter what's going on inside, you just like need to return the type shirt color. to evaluate the closure later if the result is needed. If this closure take any parameters, it will be between these two bars. We have seen seen them a few times before as well. So this is how to use it. Yeah. Okay. Closure type inference and annotations. There are more difference between functions and closures. Closures don't usually require you to annotate the type of the parameter or the returned value like given function do. Type annotation are required on functions because the types are part of the explicit interface exposed to your user. Defining this interface rigidly is important for ensuring that everyone agrees on what type of value a function uses and return. Closures, on the other hand, aren't used in an exposed interface like this. They're stored in variables and used without naming them. Expose them to use of a library. Closures are typically short and relevant only within a narrow context rather than in any arbitrary scenario. This limit context, just kind of like this. So I don't know, it feels like something like a lambda function, but like in Python there's no clear distinguish between like the two. This limit context can infer and also closure means other things in Python as well. I can infer the type of a type annotation if we want to increase the explicitness, for example, like this. Annotating type of a closure would look like a definition in this. Yeah, it looks very like a. We have this and then return num and there's U32. It's like that. Okay. Type annotation is added. The syntax of closure looks more similar to the syntax of functions. Define the function that add 1 to its parameter and then closure that has the same behavior for comparison. So this is function. Like this. Let would be, this would be a closure because it can be assigned to a variable. Be like this. And then, just comparing the two. Okay, so you can be so minimal like this as well. First line show a function definition, second show a fully annotated one, the third one remove the type annotation, the fourth line remove the brackets. Optional because the closure would have only one expressions. These are all valid. Line v3 and v4 require the closure to be evaluated to be able to compile because the type will be inferred from the usage. Using either type annotation or value of some type to be insert into VAC for Rust to be able to infer the type. For closure definitions, the compiler will infer one concept type for each of the parameters. Example closures. So this will have a problem because these two types are conflicting each other, isn't it? You have the string value the compiler will invert the type of X and return the type of closure to be a string. Those type of lock into closure in exam, get type error when we tried the different type with the same closure here for number 5. So yeah, we can't do this. It's not like Python, you can't do anything with different types. Yeah, so capture a reference for moving ownership. Closure can capture values from their environment in 3 ways, which they're actually mapped to 3 ways. The function can take a parameter borrowing immutably, borrowing mutably, and taking ownership. The closure will decide which of these to use based on the body of the function. So I'm gonna mess with this. Vector 1 to 3. Before defining closures, list, and then now I have only borrows is a closure, just print line. And then before calling closures is that, and then call only borrows after calling closures. So illustrate that a variable can bind to a closure definition, and then call. So this list we didn't pass it into it. So so it all works. It's just like borrows over. So I guess these are all immutable reference because we have multiple immutable reference lists at the same time. It's still accessible from the code before the closure definition. After the closure definition, but before the closure is called. So yeah, all of them are immutable borrows, I think. So if we change it to mute, so this is mutually, so we do a push, then so it will just determine it, the compiler will determine it by itself because this is mutable. So after calling it is also mutable because it's a mutable reference. So another thing is so adding a print line. Wait. We don't use the closure again after the closure is called. So the mutable borrows ends. Between closure definition and the closure call, the immutable borrow to print isn't allowed because no other borrows are called. Because we borrow here. So if we print it here again, then there will be a problem. Because this is a mutable borrow, and then after that, we don't have. Well, we do print it, but it looks fine. Longer print line between the definition. This is the definition. Captures a mutable reference to a list. We don't use the closure again after the closure is called. So the mutable borrow ends. So because this is a mutable borrow, so this is the mutable borrow territory. You can't have an immutable borrow here, then it will go crazy. If you want to force the closure to take ownership of the value using the environment. So how to give the ownership to the closure. Even though the body of the closure doesn't strictly need ownership, you can use move keyword before the parameter list. When passing a closure to a new thread to move the data so it is owned by the new thread. It will be further discussed in chapter 16 and when we talk about concurrency, but for now, so spawning a new thread using a closure that needs the move keyword. So for example, what we're doing here, we are using the thread now. We will spawn a new thread. We have to use the keyword move here. So print join wrap. So this is the join and wrap is kind of like the multi-threading kind of operation, but here we have to use the move keyword because then it will take ownership and bring it to the other thread. The move keyword at the beginning. And they finish before the rest of the main thread finish, or main thread might finish first. If the main thread maintained ownership of list but ended before the new thread and dropped the list, then the immutable reference would be invalid. Therefore, the compiler requires that the list to be moved into the new thread. That's why we need the move, because the main and these become two different threads, and we don't know which one finished first. Moving captured value out of closure and function. This is such a huge chapter. This is only the first section. Once the closure has captured a reference or captured a ownership of a value from the environment where the closure is defined, so the code in the body of closure defines what happened to the reference or the values when closure is evaluated later. So what happened if you give something, like give the closure ownership of something? So a closure body can do anything of the following: move a captured value out of the closure, mutate the captured value, neither move nor mutate the value, or capture nothing from the environment to begin with. So what's going on here? The way closure captures and handle values from environment affect which traits the closure implements. Traits are how functions and struct can specify what kind of closure they can use. Closure will automatically implement 1, 2, or 3 of these functional traits. So we have fn1s, which apply to closure that can call once. All closure implement at least this trait because all closure can be called. A closure that moves captured value out of its body will only implement function once and none of the other function trait because it can only call once. So everything it captured, it will be called once, and then everything will get out. This is because it's only called once. Function mute applies to closure that don't move captured values out of the body, but that may mutate the captured values. Multiple reference one before. This closure can be called more than once. Fn applies to closure that don't move captured value out of the body and then don't mutate captured values. As well as closure that capture nothing from the environment. Can be called more than once without mutating the environment, which is important in case this can occur multiple times concurrently. So, unwrap or else method on option. So this is how it looks like. So this is the function unwrap or else. Then so we have the where function ones would be a match itself. So it would only be called once, and then you'll push out something. You like none will be pushed out that function that we've just got, and or the sum type. Yes, but it needs to return t. So this function needs to give back a t. So it matches here. Generic type parameter f here. The f type is the type of the parameter name. F. So f. Sorry, it's not a function. It's a closure. The trait bound specifically on a generic type f is this. F must be able to be called once, take no argument, and return a t. So this closure need to be called once and return t. Using the func once in the trait bound express the constraint that unwrap or else is only going to call f at most once time in the body of unwrap or else. We can see that if the option is sum, of f won't be called at all, but if option is none, then f will be called once. Because all closure implements fn once, unwrap or else accepts the most different kinds of closure and is as flexible as it can be. Functions can implement all three of the fn traits too. If what we want to do doesn't require capturing a value from the environment, we can use the name of the function rather than a closure. Yeah, because it also fulfilled this rule. It had the fn once, and also it doesn't capture anything. The name of a function rather than a closure. For example, we can call new, get new empty vector if the value is none. Okay, now look at the standard library method sorted by key defined on slices. To see how differ from unwrap or else, it used fn mute instead of fn once. To a value of type k that can be ordered. It's useful when you slot a slice particular attribute. List of rectangular instance and sort by key in order order them by the width. So we have rectangle. We also have the main here. So mu is this list, and then this list we want to sort by key. So let's look at yeah. So this is how it works. So sort by the width, from smallest to the biggest. So we can look at how it's sort by key is implemented. Yeah, it takes the it takes a closure that take the r, which is the rectangle, and then we sort by the r dot width. Yeah, so rectangle means so it has a fmu closure. It's called the closure multiple times, one for each item in the slice. It doesn't capture, mutate, or move out anything from its environment. It meets the trait bound requirements. example of a closure just implement just the fn1 trait because it moves the value out of the environment and the compiler won't let you do that. The sort operation is a mutable list like did string from by key code key, so operation dot push value dot with. So this will, compared to before, it would mutate this list. So convoluted way, try to count the number of times sort by key get called. To discount by pushing a value or string from the closure environment into the sort operation vector, the closure captures value and then move value out of the closure by transferring ownership of value to the sort operation vector. The closure can be called once. Trying to call it second time wouldn't work because value would no longer be in the environment to be pushed into sort operations again. Therefore, this closure only implement fn once. And we try to compile this code, we will get the error that value can't be moved out of the closure because the closure must implement fn mute. Value has type string, which is not implement the copy trait. Error points to a line in the capture body that moves value out of the environment. To fix this, we need to change the closure body so it doesn't move values out of the environment. So for example this, so maybe value.copy. Keeping a counter, yeah, or use number. Keep a counter in the environment and increment value in the closure body is a more straightforward way. Let mu, so this will stay inside, we won't pass it out like this. Worked with sort by key because it only captured a mutable reference to the operating counter and therefore called more than once, can be called more than once. Fn traits are important when defining or using functions or types that make use of closures. This is super complicated. I want to do some exercise to make sure that I understand it correctly. Do they have any? They only have iterators. They don't have this closures. So we can't. But yeah. Operations. I hope we would get some chance to practice this in the future because this sounds a little bit complicated. But maybe when we look at iterator, it will also explain a little bit of things. So let's move on. Processing a stage of items with iterators. So iterator, we have a vector. So we can call this a dot iter, and I guess it will give us a iterator. Yeah. So val in iter, you can print, got that. It's like a for loop. Use it in a variety of ways. Iterated over an array. So in language that doesn't have iterator provided by the standard libraries, you would likely write this by using index. Yes. C territory again. Using that variable to index into the vector to get a value. Handle all that logic for you. Cutting down repetitive code you could potentially mess up. For example, off by one error and then try to access some memory out of scope. Iterator give you more flexibility and use this same logic, different kind of sequence, not just data structures you can index with. It's quite good. And also anything can be an iterator. Like it doesn't need to be something like a vector. It could be just like, you know, in Python we mess with it a lot, right? To like teach people so we can like generate a random number every time we go to call or something like that. Iterator trait and the next method. So now we have iterator, type item. So we have the next, so they will have the next function method. Then it will take the mutable reference of self and then it will give back some item. This definition uses syntax type item and self item, which are defined and associate the type with this trait. We will talk about that more in chapter 19. It's getting more and more complicated. But now, all you need to know is that the code say implementing the iterator trait requires that you also define the item type. And this item type is used in the return type of the next method. Right. So that's why we need to define it here. Iterator trait only require implementer to define one method. The next method returns one item of the iterator at a time. When iterator is over, then we would return none. So that's why I returned some, because it's an option. Yeah, it's an option. So iterator demonstration, we have 1, 2, 3, and then we create an iterator, then some, then it will be none. If we call the next method that consume the iterator. Oh wait, is there any interesting thing here? Oh, notice that we need to make mutable. Yeah, here. Calling next method on the iterator changes the initial state of the iterator. That's why we need the mutable reference. Could consume use of the iterator. Each call to next eats up an item from the iterator. Don't need to make v1 iter mutable when we use a for loop, because the loop will take ownership and then it will make it mutable behind the scene for us. That makes sense. The values we get from the call to next are immutable reference to the value in the vector. The iter method produces an iterator over immutable references. If you want to create an iterator that take ownership of v1 and return own that value, we call into iter instead of iter. If it's mutable reference, we call itermute instead of iter. So there's 3 different kind of iterators, and we have to be clear about which one are we talking about. Methods that consume the iterator. Iterator trait has a number of different methods that with default implementation provided by the standard library. You can find out about these methods by looking into standard library API documentation for iterator to understand more. Some of these methods are called the next method in the definition, which is why you're required to implement the next method when you implement the iterator trait. So there are like Boolean methods for iterators. Well, default implementation. Okay. Method that call next call consume adapters, because calling them use up the iterator. One example is some method. Take the ownership of the iterator, iterate through the items by repeatedly calling next. Consume the iterator. As it iterate through, it add each item to a running total and return the total when it's completed. It's the sum method. So that's why, okay. So total is 6, yeah. We aren't allowed to use this again because sum has take ownership. of the iterator, and it's gone, and it's consumed, it's used. Methods that produce other iterators. Iterator adopts a method define an iterator trait that doesn't consume the iterator. Instead, they produce different iterators by changing some aspect of the original iterator. So for example, a map which takes a closure call to each item iterated through, the map method returns a new iterator that produces the modified items. The closure here creates a new iterator in each of them from the vector incremented by 1. So this one, in this map method, we put a closure in, and this will just add each one of them by 1. But this one will create a new iterator. But there's a warning. To do iterator are lazy and do nothing unless consumed. So it doesn't do anything. The closure specified never get called. So because it's lazy, the warning reminds us why iterator adopters are lazy. We need to consume the iterator here. Fix this warning and consume the iterator. We use the collect method, which we used in chapter 12. This method consumes the iterator and collect the resulting values into a collection data type, so maybe a list or something, a vect. Because the result of iterating over the iterator and then returned, and then map it into a vector. The vector will end up containing each of the item original vector incremented by 1. So we have 2, 3, 4. Because map takes a closure, we can specify any operation we want to perform on each item. Sorry, I'm super tired. I just came back yesterday very late. So yeah, a lot of times like closure are used together with iterator. Chain multiple calls to iterator adopters to perform complex actions in a readable way. But because all iterators are lazy, you have to call one of the consuming operator method to get the result. Yeah. So either you call something like sum that will consume it, or you call something like collect at the end after map to consume them. Using closure that capture the environment. Many iterator adopters take closures as argument, and commonly the closures we have specified as argument the iterator adapters will be closures that capture the environment. Filter method will take a closure get an item from the iterator and then return a bool. If the closure returns true, the value will be included in the iteration produced by filter. If closure returns false, then it won't get included. Capture the shoe sizes. So we have shoes, we have size and style. Shoes in size, it will return. So it will become a iterator that have ownership. And then we apply the filter, and then we'll collect at the end. So if the size is equals to whatever shoe sizes that we want, that will be included. Yeah, like that. The shoe in size function take ownership of the vector of shoes, and the shoe size is the parameter. Shoes in size take ownership of the shoe. Yeah, the vector of shoe, and shoe size is parameter. Yep. The body of shoe in size we call into iter to create an iterator that take ownership of the vector. Then we call filter, and then the closure captured the So it does collect and then return as a vector. The closure captures compare the values. Yes, keep only choose of the size specified. Get back only choose that have the same size. Okay. This is how it get used, and this is why we introduce closure right before we learn about iterators. And then 2 more chapters, 2 more sections, then we finish chapter 13. And do we want to do some rustlings of because we have iterators that we can work on. It depends on the time. Let's see. I have a very busy afternoon today, so I don't want to be streaming too much. I'll try to pick up the pace again, because again, like I just came back, I'm super tired, and I have things to do this afternoon, so I don't have much time today. I'm sorry, but we are trying to go back into a constant pace that we learn something every day, and then this is what I'm gonna do. Try to be consistent, but I'm going away again this weekend, which is very, very difficult. Okay, improve our IO project. We are improving our IO project from chapter 12. But before that, maybe we'll take a small break, because again, like I'm falling asleep. So give me like a few minutes break, and then we will come back. Okay, let's come back and go back to our IO project, which is here. Okay. New knowledge about iterators. We can improve our IO project using iterators to make it cleaner and more concise. removing a clone using iterator. Edit the code. Where was this? Config build. Argument. Ooh, okay. On a slice of string value and create an instance of config struct by indexing into a slice and clone the values. So refresh what we were doing. So in the config build, so in our library here, config, when we build, enough argument. So we're taking in this arguments as string. So so we have to take the clone here because these are references, and then we would clone it there for simplicity, allowing the config structure to own those values. We have reproduced the implementation. Yeah, I was like, here, found it. Right, so, oop, can you hear my washing machine? Sorry about that. I also have lots of laundry to do this morning. I just came back from my trip, and then there's lots of laundry to do. I have to do it in 2 batches. This is how much laundry I have to do. Okay. So yeah, we have. So how can we improve this? Not to worry about the inefficient clone call, because we would remove them in the future, and now we're doing it. I need clone here because we have a slice of stray elements in the parameter args, but build function doesn't own args. Return ownership of a conf instance, we need to clone the values. So the conf instance can own the value. Now, with iterator, we can change the build functions to take ownership of the iterator as its argument instead of borrowing a slice. We'll use the iterator functionality instead of the code that checks the length of the slice and index into specific locations. Iterative access the value. Once the conf build take ownership of the iterator and stop using indexing operations. That's why we can also avoid this like indexing referencing nightmare with using iterator, which is great. I think someone mentioned this like in one of the rusting exercises I was struggling with, but I haven't learned it, so yeah. Remove the string value from the iterator in the conf rather than calling clone and make new allocation. So how we do that? So main, it looks like this. So we call build and then put args. So instead of args, maybe we'll put a iterator of args. Maybe change the start of the main function. So yeah, so what do we do here? Oops. Build. So instead of build args and then unwrap or else, we would change it into args dot unwrap or else error. So it's like this now, but there's a problem, of course. Now we have an iterator because n args will give us an iterator. Rather than collecting the iterator values into a vector and passing a slice. So this is what we were doing here before. We were collecting them and making the vector and put it in here. We would just pass this in instead of collecting it here. So let's copy this, config here, blah blah blah. I think I only need to change. Oh no, this is the closure. So this will, the whole thing is either let config equals to this. So now I want to pass in this here. but then I also have the unwrapper else, and all these will be moved. Oh no, yeah, it's fine. So I just, instead of collecting, I just shove this in. Don't need this anymore. This is what I'm going to do. Just shove this in. So. Now we have an update, of course, the build, the config build. Oops, what's going on? In your IO project, let's change the signature to look like this. Yeah, we haven't make enough changes to make it compilable yet. So let's come back here. Let's change this so it doesn't take the arcs. It should take so it's so it's like that. Okay, it's a bit complicated. So we'll do it like we'll do it like this. Oh no. Why? Okay. We'll replace this with this. Yes, now it makes sense. So beautiful reference to the iterator. Now it's an iterator. It will take item will be the strings, because this is what we have. Result will give back a is a config like, or the error in, like, string. So this is the error branch that we probably need to change this in the next step. Function shows the type of the iterator, returns this, and then any type implementation iterate returns a string value. It's a generic type of the trait bound. So we're using a trait bound here. If it has the implementation of an iterator that the items are string, that's okay. then it would be our mutable argument, which is what we would have. Instead of just end string. Usage of input trait syntax discussed. So we just learned it before in chapter 12. Or no, chapter 10, okay. Yeah. Now we're taking ownership of args, and we'll be mutating args by iterating over it. You can add the mu keyword into the specification. Of args parameter and make it mutable. Okay. Yeah, we have to change it, so we have to put the mu using the iterated trait method instead of indexing. Now it's iterate trait, we can call the next method on it. So we use the next method. So we'll do this instead. Here. So query it match, so we would just call the next on this. It will give me either this or a none. Then we have the error, doesn't get a query string. Yeah, we don't even have to change the check the name and the length anymore, because if it doesn't go through this too, then probably it's not long enough. Oh wait, what about the first one? Oh yeah, we call the next to get rid of the first one. Yeah, because remember the first one just the function self name itself, right? The process name itself. So we're next. And then we come in here. It's fine if it's like, if it doesn't have anything, then we just already, so we don't have to check the length anymore. No case, and then the rest is more or less the same. Yeah. The first value is the name of our program. We want to ignore it, and so that's why we call next and do nothing. And the second we call next to get the query, and then we got the match. If not, then we'll have some errors. Make the code cleaner with iterator adapters. We can also take advantage of the iterated search function in our IO projects, which is reduced here. So this is one thing we have fixed. It should still work, so we can check now. Maybe just do this. It should compile and work. Yep, it still works. And then next modification. So that we have the search. Where is our search? Search here. Yep. Yeah, my screen keeps like flickering, changing the brightness and stuff. Is very weird. Right. Okay. So in search we have the line in search.lines. This is what we did before. More concise way by using an iterator method. Let us minimize, because yeah, the for loop can be replaced, isn't it? So we can change it into something like that. Contents.lines, and then we can just apply the filter on it. Yeah, because content.lines will give you an iterator, right? So we can replace this for loop. This. Oh, we don't even need to use this this result anymore, because we just return it directly. We don't need this anymore. I have to use a for loop to collect them. So this will be iterator, then we apply the filter, line, contain query, we include them, collect them, and return it. So this is what we do. It's easier than looping over it and then use the result to store it. I sometimes do things like that in Python, just because it's more straightforward to think it that way. But yeah, we can make use of the functional programming to make it faster. You can do that in Python as well, but it's not, instead of the method, like you have to use map or filter like built-in function. So that's why it's not that popular. This looks more like your thought is just like go through this, but in Python you have to put it in the filter at the front, which is a bit intuitive to think. Next logical question is which style you choose. A bit tougher to get the hang of it at first. Yeah, it's just not that intuitive for a lot of people. There are two implementation truly equivalent. Intuitive assumption might be the one more low level loop with faster. Oh, okay. Performance, yes. Most Rust programmers prefer to use the iterator style. It's a bit tougher to get the hang of it at first, but then you feel the various iterator adapters and what they do. Iterator can be easier to understand instead of fiddling with the various bits of looping and building new vectors. Yeah, that's why I really love they can, like, you can just chain it like this, compared to Python, which is different. You can just think of it like, now I can filter and collect. This is, yeah, more good. Like, I don't know. I wish I can have a built-in function doing that. Another Python loop is very slow. Away some of the yeah, okay. Performance. Loop and iterators. Bench search for bench search iterator. So iterator seems faster. Look for the in the word. slightly faster. We won't explain the benchmark code here because the point is to what's going on. Iterators, those are high-level abstractors, get compiled down to because it got taken care of. So usually it's like if you are writing in a language that is like not C, then like it's better to use built-in like or things that taking care of the thing for you because they usually are optimized. If you write your own for loop and stuff, it's of course not as optimized as using iterator. You compile roughly the same code as you write down the low level zero cross abstractions. What you don't use, you don't pay for. What you do use, you couldn't hand code any better. So, yeah. So it's convenient. It's you get lots of things taken care of for you, and it doesn't cost you time. So, audio decoder. Change to do some math on 3 variables. So you use iter is zip and a map and a sum. I'll declare the variables within this example but not giving them any values. Still a concise real-world example of how Rust translates high-level idea to low-level code. Calculate the value of prediction, iterate through each of these 12 values in coefficients and use zip method to pair the coefficient value with the previous 12 values in buffer. Buffer.length. Where were I? Yeah, then for each pair we multiply the values together and then sum all the results and then shift the bits, the sum to the right. Audio decoder to prioritize performance. Down to the same, okay. No loop at all corresponding to the iteration. Rust knows that there are 12 iterations. Unroll the loop. Unrolling is an optimization that removes the overhead of loop control code instead of generating repetitive code. So what it does is that because this one is like only 12 and it's kind of it doesn't change, everything is written in the code, so Rust will just do it 12 times. So because doing it 12 times actually is faster than having a loop control code and do those things. So yeah, of course by hand you don't want to do it 12 times, but the compiler can do that for you. Storing the registry, accessing value is very fast, no bound checks. On the array access runtime, makes the resulting code extremely efficient. Use them without tears. Okay, so this is just like convincing you to use more because you don't sacrifice time. So use more iterator and Clojure. They are good for you. So Clojure and iterator are Rust feature inspired by functional programming language ideas. They contribute to Rust capability to clearly express high-level ideas and low-level performance. Now we have improved the expressiveness of our IO project. So then next time we'll look at Kaggle to help us share the project with the world. So we'll talk about packaging with Kaggles and Crates.io, which is cool. Yeah, we have still more concept to go, but this is good. But I think to get use of this, we'll have to do more practice because this is quite a new concept to me. Not iterator and like have high level, but like low level kind of things that yeah, how it fits into the grand scheme of things, and yeah, take some time to get used to. It's good. Hope to see them more. I don't think I have the energy and the time to do the wrestling exercise today. We'll just save up some more, then we can practice at the end. Maybe yeah, we'll save off them at the end. Yeah, so next time we'll look at chapter 14, probably tomorrow. I'm very tired. Like I said, I'm tired and busy today. Tomorrow will be better. Tomorrow we have more time. Hopefully. Fingers crossed. And see you tomorrow. Have a good day. Good wherever you are, or maybe good night, good day. Or if you watch it in the future, enjoy. Yeah, thank you so much and see you in the next one.